All right, so I'm going to start a new topic today. I'm going to start talking about twisting things. Uh, it's in chapter 5. And before we begin or get started, anybody got any questions or comments or anything you want to talk about before we begin? All right, well, then let's talk about twisting stuff. What we're going to do today, you'll find in the first two sections in your textbook, in chapter 5, sections 1 and 2. This deals with the torsion of circular shafts. And we'll emphasize we are just going to look at twisting shafts that have circular cross sections. In fact, what our goal today is to come up with a formula that if we have a shaft with a circular cross section and we apply a torque or a twisting moment to that, we can calculate the shear stress in that shaft. The formula that we're going to come up with today is only going to be valid for circular shafts with circular cross section. So the formula that we derive won't be valid for a shaft with a different cross section. In fact, you'll see circular shafts are actually pretty simple in the end. Anyway, we're going to derive this formula. It's just a matter of plugging in a formula. If you twist a shaft that has a cross section that's not circular, it's not just a matter of plugging in a formula. It's a much more involved, complicated problem to solve. And I know I have a few aerospace majors in here. You will encounter twisting non-circular shafts in the first structures class, Aerospace Structural Analysis 1. Some of you others may be in civil or mechanical. More than likely, somewhere in some structures course in your curriculum, you will encounter twisting non-circular shafts, but I just can't tell you specifically which class that would be in. But somewhere down the road, you'll probably revisit this. So let's start with basically defining what we mean by torsion. Also, you'll see this referred to as torque, also a very common name. It's a moment. It's a moment that twists a member about its longitudinal. I can spell this longitudinal axis. For example, if we look at this shaft or bar that's got a circular cross section, be consistent with what we've have done in the past. The longitudinal axis, we're going to stick with referring or calling that the x-axis. So if we apply a moment or a torque, we'll call T. If I can show a picture here, I'm twisting this pin. That's what the moment is about, that longitudinal axis. It's going to twist this thing, and it's going to cause it to deform. It's going to twist and rotate, and it's going to cause a shear stress on the cross section. And as I said a second ago, that's our goal. And so if we cut this thing and look at that cross section. Maybe say this is here at A. So if we're looking at this cross section here where we cut it, so we've got this torque, and when we look at this cross section, we're going to see a shear stress tau is going to be acting on that cross-sectional area. Remember, the shear stress is caused by a shear force that is parallel or tangent to that surface area. And that's what we're after today, is how do we calculate that shear stress on that cross-sectional area. All right, there's a couple of different ways we could get there. The approach that I am going to take is slightly different than the approach in the textbook, but that doesn't mean you shouldn't look at how he derives this in the textbook. In fact, being a little bit different might be good in that some people see things a little bit differently. So the way that I come up with this, if it doesn't make perfectly good, clear sense to you, read about this in the textbook and see how he describes it, and maybe it might make more sense to you than the approach that I'm going to take. All right, so let's say we got this big circular shaft here. Just draw a straight line. Yeah, that's not too good. Now, use your imagination. Pretend like that's circular. And let's say we got this end back here and it's fixed. Right? So it's like attached to the wall at that end. Again, our x-axis is our longitudinal direction, And let's see if I can draw a straight line here along the shaft. That's not too bad. So the length of the shaft we'll call L. And let's say this point here is point A. So if you draw a line along the outer surface of this circular shaft from this end to this end, we're going to define the radius as C. So C here is the outer radius. If we're talking about just some arbitrary radius, so if we go some arbitrary distance from the center, we're going to call that rho. So rho would just be an arbitrary radius somewhere between 0 and C, but we're defining C to be the outer radius. If we apply a torque to this circular shaft, it's going to twist. It's going to rotate. Point A here is going to move down some point here, I'll call A prime. And now I'm going to turn around, see if I can draw another straight line here. Yeah, sort of straight, not exactly. Pretend like it's straight again. But that's what's going to happen if you look at that cross section. When you apply that torque, it twists and rotates around. This point's going to move down. Now, if you look along the side of this thing, at this point here, it doesn't move, right? It's affixed, it's attached to the wall back there. Well, this angle here that I'll put below there because it won't really fit. This is what we call our shear strain. So this angle gamma is our shear strain. Remember, go back to when we first talked about shear strain. We said it was the angle of distortion. Well, that's what that angle is. It's the angle that member is distorted. Now here on the cross section, right, it's going to rotate through some angle, and it's going to be, maybe I should have drawn my picture a little bigger. But this angle on the cross section, we're going to call it phi, and we refer to that angle as the angle of twist. Right, two different angles. Phi is the angle if you're looking at the cross section, how much it rotates. If you're looking at the side longitudinally, that angle that it's distorted, we're going to call gamma. That's our shear strain. All right, so what we're going to use is our small angle approximation again. So if this angle gamma is very small, then this arc length here, A prime, we're going to say is essentially straight. So same thing we've done in the past, we're neglecting the curvature. You know, if you take a small enough piece of a circular arc, it's essentially straight, and then that's what we're doing here. So keep that in mind. At the end, the formula that we come up with is only going to be valid for small deformation. So if you took a circular shaft like this and twisted it so that it rotated around 45 degrees, our formula is not going to be valid. Right? It's only going to apply to really small deformation. Right? And we also know that gamma is essentially equal to tangent of gamma, which again, if we're assuming this is straight, tangent being opposite over adjacent would be whatever the length of this side is divided by the length. So that essentially, assuming straight line, would be equal to gamma times L. Right? Again, this comes from assuming small angle. But essentially now we're going to do the same thing, but we're going to look at the surface area. Right? If phi is very small, then phi is essentially equal to the tangent of that angle phi. Now here, looking at this angle, this is the angle of twist phi, tangent being opposite over adjacent, opposite would be our assumed straight side, divided by the outer radius of that circle. So if you solve that for A prime, it's equal to phi times C. So what we have here is, I forget the name of this, one of those mathematical properties. If A equals B and A equals C, then B must be equal to C. I forget what, somebody remembers the name of that. It's not transitive property, is it? I don't know, I forget. We'll call it the common sense property. If this is equal to gamma times L and it's equal to phi times C, then gamma times L, right here, is equal to phi times C. Now, if we solve that for our shear strain, gamma, then it's equal to phi times C over L. So we've got a formula for our shear strain. Now, ultimately, remember, we're headed toward finding shear stress, but we'll get there. This is where we're going to, our start anyway, is we have something that tells us what shear strain is. Now, just in general, And typically when you're looking at twisting circular shafts, you're going to be interested in this the outer surface, and this would be the shear strain at that outer surface. But if you wanted to know what the shear strain was, just some arbitrary radius, you could go through and do the exact same exercise. I'm not going to go through it. It's some arbitrary radius rho, and you would get the same result, but instead of C, the outer radius, you would get just some arbitrary radius rho. This is actually going to be the maximum, right? So gamma max is equal to phi times C over L. This is at the outer surface, where rho is equal to C. That would be your maximum shear strain. Right in the center is 0. Right? If you look at that cross section, this circular cross section, you twist it, point right in the middle doesn't move. The shear strain there, when rho is 0, shear strain is 0. All right. So questions at this point? All right. Let's see. I'm going to go to a new page. Somebody speak up if you're still writing something.
I'm still writing.
Okay, we'll take a second. So while we're waiting a second, if we know shear strain, right? So if we've got shear strain, we've talked previously about a relationship between stress and strain, and it had a name. Anybody remember? It was a relationship between stress and strain. We looked at both normal stress, normal strain, shear stress, and shear strain. Anybody remember the law was called?
Hooke's law?
Hooke's law. Right. So that's how we're going to get from stress, or from strain to stress. All right. Are we good now? Okay. Anybody else? All right. So let's go to our next step. Let me rewrite what I had up here. So I had the shear strain. Gamma is phi times rho over L. Again, it's just for some arbitrary radius, rho. Come on, focus, sorry. There we go. All right, so let's multiply both sides by G. So multiply the left side times G, multiply the right side times G. Rho over L. All right, nothing wrong with that mathematically. But you recall Hooke's law. Yeah, I think that's about it. I think it has an E in it. Hooke's law for shear. So in Hooke's law for shear said tau is equal to G times gamma. Shear stress is equal to the modulus of rigidity, or shear modulus, times the shear strain. So this thing on the left side, right, this is shear stress. So I know shear stress is G times phi over L times rho. that would be for, again, any radius between 0 and C. The maximum is going to occur at C. So it would be G times P over L times C. This is at the outer surface. So we have a formula now, not quite what we ultimately want, but we're getting there. We now have a formula for shear stress. It's in terms of this angle of twist phi. Now, we want to do better than that, and we're going to do better than that in just a second. But I think it's worthwhile to at least sort of pause a second and note that the shear stress is linear. It varies linearly with respect to the radius rho. If you look at the cross section, and let's say if we're twisting this thing this way, if you look at that surface area out here at the outer surface, that's where you're going to get your maximum. But it's a linear relationship, and if you looked at the stress distribution, it would look like this. You get shear stress is 0 right in the center of that circular cross section. This also sort of illustrates what you'll see when we start solving a bunch of these problems. And you may not have really thought about it or thought about why, but a lot of shafts that have torque applied to them, vast majority of them are circular, which reason for that being they're the easiest to analyze, so that makes it easy to design and analyze. But you'll also, if you start to notice, you'll see a bunch of them are hollow tubes. And this is a good illustration of why you see a bunch of hollow tubes. You look in your car, your transmission shaft, it's a hollow tube. Reason being, the shear stress right in the middle is 0. So this material that's right here close to the center, it's really not doing anything. It's not taking any load. And so you can make it just as strong, much lighter, if it's hollow, and opposed to being a solid shaft where you got all this metal here in the middle. It's really not carrying any of the load. All right, so I digress a little bit. Now, let's get back to our formula here. It's a good formula, but we would really like our formula to be in terms of the torque that's applied as opposed to this angle of twist. You tell me you apply 10 foot-pounds of torque to this shaft. Right now, we would have to go calculate what that angle is, plug that in to get the shear stress. We want a formula that relates shear stress and the torque that's applied as opposed to that angle. So that's where we're headed next. So we've basically, phase 1, we're halfway there. Now we got to take this formula and try to get rid of phi and get the torque in there somehow. Or this formula in terms of rho. All right, so that's where we're heading. So if we're looking at this shaft, and let's go different this time. So we've got the shear stress, tau, acting on that surface. Well, if this thing's in equilibrium, then the shear force that's associated with this shear stress has got to cause a moment equal to whatever the torque is, right? Equilibrium says that some of the torque's got to add up to zero, right? Some of the moments equal zero. So the shear forces must produce moment equal to whatever this torque that's applied. All right, so I'm going to draw a bigger picture so we can see this a little clearer. Yeah, I'm not a great artist. All right, so we've got this torque applied. And on this surface area, we're going to have a shear stress. Now, we know from previous discussion on shear stress, tau equals V over A. V here is the shear force that's acting over that area. So that means the shear force is equal to the shear stress times the area that it acts over. So we're just taking our formula for shear stress and solving for shear force. And you get the force by multiplying the stress times the area that it acts over. So if we go up here some arbitrary distance or some arbitrary radius rho away from the center, and we look at some infinitely small differential area. Basically, we're going to take our circular cross-sectional area, break it up into infinitely many little rectangles. We call it dA. There is a shear force that's acting over that differential area. I'm going to call it dV for the differential shear force. So that's our shear force V that's acting over that little bitty area that we call dA. Well, the same relationship applies, right? I can get the shear force by taking shear stress and multiplying times the area that it acts over. So it would be tau times dA. All right, so now we're going to get the moment that differential shear force causes. So we'll start with, we'll call this the differential torque. We'll call it dt, right? It's going to be whatever that differential force is times the distance away, because that's the perpendicular distance from that axis. So it would be rho times dV. And all this is moment equals force times distance. But this is the moment caused by that differential shear force would be equal to that differential shear force times that distance away from the axis. But I know from over here that differential shear force is tau times dA. Excuse me. And let's see, I want to substitute in for tau. I reckon we'll do that for. What we're going to do now is what we found for tau up here. Yeah, better move that down a bit. Previously we know tau is G times phi times rho over L. So I'm going to substitute that in. G times phi times rho over L times dA. Just taking our previous formula for shear stress and plugging in here for shear stress. Now to get the total torque, we integrate. So we integrate both sides. And I'm gonna, we'll just write it like this for now. G times phi. I got rho squared now. Rho times rho is rho squared. So on the left side, we're going to get the total torque. On the right side, I can factor out G, phi, and L because those are constant with respect to we're integrating over this cross-sectional area. The only thing that varies is rho. Obviously, the radius changes. If we go out, closer to the center or further from the center, rho is not constant. But G is the material property. It's the modulus of rigidity. Phi is the angle that cross-section rotates when that torque is applied. L is the length of the shaft. Those are constant with respect to where we're at on that cross-sectional area. So we can factor those out. Now, this integral here may or may not recognize, but it's the moment of inertia. And so this integral here, rho squared dA, this textbook does what most textbooks do, as far as notation-wise. They call this J. It's the polar moment of inertia. Which all that is, it's the moment of inertia about the x-axis. It's the cross-sectional area, moment of inertia about the x-axis. So just make note here. If you're looking at this circular cross-section, this area, J is just Ix. Now, why J is used instead of Ix, I don't know. I can't tell you, but I can tell you is that's what, more often than not, it's the notation that's used for this moment of inertia. I have seen very few mechanics and materials texts that actually do not use J and they call it Ix, but most of them use J. This one does, so that's what we're going to use. All right, and we're going to come back and talk about J some more, the polar moment of inertia, in just a minute. But for now, let's just accept the fact that that's what this integral is. And so we get the torque here is G times phi times J over L. We're getting close now, so be patient. I know, I try to spend the majority of time solving problems, and as little time as possible deriving formulas. But there are a few formulas that you really need to see where it comes from, and this is one of them. I feel like it's important for you to see how we get this formula at the end, rather than just tell you, hey, here's the formula, go plug in the formula to get the shear stress. Anyway, so bear with me. That's, again, what we're spending most of today doing is getting this formula. On Monday, we're going to apply the formula and actually solve some problems. All right, so am I good? Everybody got everything you want off of this page? Speak up if you need a minute. I'm going to show you how to calculate J in just a minute. There's a formula for that. If you look in your statics textbook, I know, and I think even mechanics and materials maybe, in statics you had a table that gave you formulas for moments of inertia for common shapes like areas and rectangles and triangles. It's not that difficult to take this and actually go through and do the integration and derive that, but that one I'm just going to show you the formula. there's a formula we just can plug in and get J. We're not going to have to actually integrate. All right. So let me rewrite this down. Here's where we're at. Torque is equal to G times phi times J over L. All right. And so just got to do a couple of things to get us there. What I'm going to do is I'm going to multiply this times rho over rho, all right, which I can certainly do that, just multiplying by 1. And now rearrange some stuff. And so if I get G times phi times rho over L times J over rho. So essentially all I did was just swap the order of J and rho there in the numerator, which is perfectly legal, mathematically wise. But this, that's tau. That's our shear stress formula that we derived a minute ago. So now I've got torque is equal to shear stress tau times J over rho. And we just solve for shear stress now. Tau would be equal to T times rho over J. Again, this would give you the shear stress for some arbitrary radius anywhere between 0 and C. Now, typically, we want to know what the maximum is. I know it's 0 at the middle. If you go halfway out, it would be half the maximum, but that material is going to start failing when the maximum reaches whatever the allowable is for that material. So what we're really more interested in is tau max BTC over J. So this is the formula we're after. And again, this would be on that outer surface where rho is equal to the radius of that circular cross section. That's where our maximum shear stress is going to be, and this is how we can calculate it. Pretty simple, straightforward, not real complicated formula. Now, if you get a non-circular cross section, it's nowhere near this simple. It's much more complex, and there's really not a formula you can just plug in. But with circular cross sections, it is. Now, I want to do one more thing before I give you the formula to calculate J, the polar moment of inertia. There's another formula that we're going to use, and you're going to see a little bit later in the textbook, to calculate what that angle of twist is. We call that phi. Now, what I'm about to do, we're going to use this later. I say later, first of next week, in section 5.4. But I think it's much better to show you where that formula comes from right now, while all of this stuff is really fresh on your mind, than wait, until first of next week when we get to section 5.4, and then have to go back and remind you of all this that we just got through talking about. I think it's better to go ahead and do it now. So just keep in mind this formula I'm fixing to derive here. Well, you're not going to need it in this section, but we're going to use it. We're going to use it later. But it's real simple, right? We know tau is G phi rho over L. We also just found out that tau is T rho over J. So this is really, really simple. Just take this formula we just derived, one from earlier, and set those two equal to each other. So if we set those equal to each other, we get G phi rho over L is equal to T rho over J. Radius cancels, and if you solve for phi, you get TL over JG. So this formula is one we're going to need a little bit later in chapter 5. Simple, straightforward formula. If you want to know that cross-sectional surface, how much it rotates, that's the formula that will get you that angle of twist. Now, just again, this is just FYI, just for comparison's sake. You remember we had this formula, delta, it's PL over AE. Right, this was the axial deformation. If you've got a shaft and you have an axial load, deformation was dependent upon 4 things, right? The P here being the load, L the length, right? This cross-sectional area, the size, and if you got a bigger bar, it's not going to stretch as much. And then E was the material. Right? Different materials are stronger. Aluminum's not as strong as steel. It's going to stretch more. Those were the 4 things that factored in or determined how much the thing was going to stretch. The load, the length, the size, and the material. But notice this is the same thing, right? This is angular deformation. And really, it depends on the same 4 things. The load, in this case, the torque and a moment instead of a force. The length, J, that is the size. The bigger the cross section, the larger the polar moment of inertia. And G is dependent upon the material. So it's the same 4 factors to determine angular deformation as they do axial deformation. It's just again, a moment instead of a force, but it's still load, length, size, and the material. All right, so last thing, and then we can stop this, is let's talk about J. Again, you can look in probably your statics book or mechanics and materials. This one, it has some formulas for moments of inertia. Might be in there. It's really not that complicated to derive, but here, I don't see where it would be of great benefit to go through and derive this. This one, I'm just going to give you the formula. Again, you can look it up if you don't believe me in one of those tables that have moments of inertia and get it. But somebody took a circle and went through and did the integration. And this is what you get. If you got a solid circular shaft, so we've got a solid circular shaft, got radius of C. The polar moment of inertia is pi over 2 c to the 4th. Units are going to be what you would expect for any moment of inertia. It's going to be length to the 4th. But not that complicated. Again, it's just pi over 2 radius to the 4th power. All right. Now, as I mentioned a minute ago, a lot of these we'll encounter will be hollow shafts. So if you've got a cross section that's hollow and has a outer radius, I'll call CO for outer, and inner radius, CI for inner. Well, to get the polar moment of inertia here, you just take the polar moment of inertia of the big solid circle and subtract polar moment of inertia for that hole. And so what you get is pi over 2. You can factor out, and it's just the outer radius to the 4th minus the inner radius to the 4th. So if you got a hollow shaft, you're just subtracting the moment of inertia for the hole. Now, one thing I'm going to point out here, because I see way too many students do this, and this goes back to bad math. Pi over 2, the outer radius to the 4th minus the inner radius to the 4th is not the same thing as pi over 2 outer radius minus the inner radius, that to the fourth power. If I had $1 every time I saw a student do that, I'd be rich and retired right now. But everybody should agree with me. This is not equal to that. Two different things. But I see students do this all the time. I don't know if it's just to get in a hurry or not careful, being careless or what, but point this out so maybe you will not make that mistake. All right, if you got a hollow tube, it's outer radius to the fourth minus inner radius to the fourth. Don't subtract the radius and then take that to the fourth power. All right, so that's how you calculate this J here in this formula. Power 2 C to the fourth. All right. So that got us to where we can now solve problems, but I'm not going to start that in the last, whatever, 3-4 minutes we got left. So this is a good place to stop. So basically we've got, at this point, there's 4 formulas that you need. Tau equals TC over J. Angle of twist phi is TL over JG, which we're not going to use right now, but we will use later. And then to get polar moment of inertia, pi over 2 C to the fourth. All right. Any questions about any of those formulas? How we got there? What any of the things in the formulas represent? Any questions? All right, so as I said, it's a good place to stop. So I'm going to start recording here in just a second. Let's give you one last chance. Anybody got any questions about anything we did today or something we did yesterday or anything? All right, well then I'll stop recording. Yeah, same as usual. If you got some questions you want to hang around afterwards, and then I'll be glad to stick around and we'll look at then. Otherwise, have a good weekend, and we'll be back Monday.